Imagine Cartesian grids. So very easy, very simple to save in data. Big, large blocks of data. We call them brick of values. I'll show you how to set that up. We can have HSPart, which would be specific to particles. If you're doing an SPH type of simulation, you don't have any grid, just particles in space. This would be something specific to use. I can help you write the software into your simulation code to actually output the data correctly. I have done that in the past with other groups. And then we have other incantations of file formats which are available. What's important is that a file format should do things like this: allow partial reads, subsettings. This will be important for parallel processing. Allow browsing, allow ingestion by the visualization software without having to reshuffle, etc. Allow random access. This is extremely important. So random access is go to time step 1000 before reading the first 999, right? And then display without discontinuities. So we have to think about all those issues when we archive our data. Of course, the archiving should provide checkpoint and restart for you. If possible, if the same file can be used for visualization, then we have only a single set of files, both for the simulation and for the analysis. Independent of the number of processors, this is very important. I've said it already. Now, there are some community-specific file formats, such as CGNS in fluid dynamics, CCSM for climate, NEC 5000 for combustions, etc. In that case, we should have no problem reading the data into the visualization software. I say we should have. When we talk about climate data, this is a difficult issue. There are multiple versions of people using NetCDF data. There are the so-called CF conventions, which are the climate F. What's the F? Climate forecast, yeah, perhaps. I'm used to saying CF. So can ParaView and Visit read CF NetCDF data? Yes, mostly. Mostly. This has to be tried, and there is an effort that I'm doing currently with some groups at ETH to read some more esoteric NetCDF data. In any case, don't make your own, and if you do, if you expect to have helps from us, consult us before you invent your own data format. Here's an example, simple, in MPI, a 2D distribution, 3x4, yes, 12 processors. Here are the ghosts, okay. But the storage is actually this. The ghost should be independent completely. If I do it with 4 processors, here are the ghosts. The image is still the same. The storage should be completely independent. Here's another example which we will use tomorrow. And your exercise will actually be exactly this, to show the ghost cells. So here we see a one-cell layer of data that is exchanged at the boundary of the processors. Here the coloring represents the processor. Okay, and in that case, Visit has reconstructed the ghost cells. So the exercise tomorrow will actually be to load this data set with 4 or 8 or 32 processors and then see that you get the right result. Silo is a very interesting data I/O library which I recommend for you to use. It's extremely well supported by the visit software. And as you can see, it reads really a large variety of data configurations, unstructured AMR, data with multiple species, with multiple material, CSG mesh data organization, arbitrary subsets, and so on. So I recommend you, you try this if you are looking for a generic library. This has the advantage that you can do parallel I/O without writing any parallel code. How do you do this? Each processor in your simulation would actually write its own independent file, and then a meta file would describe the global organization. This is a common practice, actually, of using every processor, of telling every processor to write its own data without caring about parallel programming. In this case, I have an example here of this BOV format, which is this brick of value. If you keep in mind the little simulation I showed on the screen earlier with 12 and 4 processors, this 2D heat equation solution. Okay, if every processor writes its own file, I end up with something like this: one file per processor. So this is the time step, step number 4, and this is processor 0, 1, 2, 3, 4, 5, 6, or 5. And each of them, you see, is exactly 1 megabyte, which means that it was exactly a block, well, in 3D, 64 by 64 by 64 by 4 bytes. They can be gzipped. That has an advantage too, because you see the file size is much smaller, and you can gzip the data at the time you are writing from the simulation. So this is very effective. I can give you source code to show you how to do this if you need help. And at the very end, you have a very small file here. You see 412 bytes. This is the content of the file. It's ASCII, so it's readable. That's what I wanted. And it tells me this is the BOV format. Here's a pattern of file names which should be read. So time step 4, and then all of those are the processor ID. The global grid storage is 192 by 128 by 64. Each of the processor contribution is 64 cube. It's float, etc. And with this, I'm able to reload my data independently of the number of processors available for the visualization. So it's very nice. When I read the data back, those are images from visit. You can see here each of the processor's contribution. Each of those little color blocks is one processor. And depending on the striding and the scheduling of my processors, I end up with different coloring here. But the data internally, globally, is all the same. Here's another example with Pixie. This is a data format I have. I didn't invent. It was invented in the US by the Energy Labs. And what I have done for the purpose of the plasma physics, I've implemented the parallel reader. So it's for the people doing physics in a torus. You can see here the shape of the torus. And you can imagine that there are multiple ways of doing data distribution in a torus. And I have implemented all those different techniques of processor to data region allocation in order to bring flexibility to the reading. The Pixie format is an HDF5 convention. So here's the key word, a convention. Just like earlier we talked about the CF data in climatology, CF is a convention. It's a set of rules that people agree upon to write their data using a particular library. So with CF, it's a set of rules for the NetCDF library. With Pixie, it's a set of rules for the HDF5 library. And if you write your data using those particular rules, then the visualization software can read it back as expected. So here we have examples where the same data can be interpreted as a regular Cartesian grid or as a curvilinear grid. And when we look at the HDF5 data with a browser, we see here the node coordinates as X, Y, Z data sets. We see the specifications of the curvilinear grid and the regular grid. This would be the Python code necessary to archive data in this particular fashion. I will distribute this code, this source code, which you can try in your own, with your own data. The VTK file formats here are described if you follow those particular links. Basically, we have those types: curvilinear, rectilinear, uniform. We have two different types for unstructured data. Polydata, which is associated with geometry, and then the regular unstructured grid in terms of finite elements. When we're going to load our data, we should inspect what ParaView has discovered about our data, and that's the metadata exactly, the type, the number of variables that are read, the number of time steps which are available, etc. Now, when we have time-dependent data, usually we don't read all time steps in memory. Otherwise, we would explode. Usually, we have options to read data at a particular time step right from the beginning, so that you don't waste time reading the time step 0, which can be very large, etc. So we'll have to look in the software for those particular options. And if we look at a particular filter of ParaView called the data object generator, we actually can see that there is a specific icon that is associated with each of those particular time steps, particular data types there. On top of this, you can have the so-called collections or composite data sets. So here, multi-block. Here's a single curvilinear block in a large composite data set. We can have adaptive mesh refinement. So this would be an example here in astrophysics of multiple levels of data. And this is the pipeline representation here inside of ParaView. So you can see that each of the levels of the data is actually visible. Now, when we talk about composite data sets and AMR data sets, there's something extremely important to understand, which is the big difference between ParaView and Visit. ParaView will read in memory everything available, the full hierarchy of grids and patches, etc. And then it will give you a filter called extract block, where you can go out and extract a particular grid. The summary is that the whole data set has been read in memory, which can be actually impossible if your data is too big. Visit does something completely different. Visit will instantiate the pipeline, will not read anything in memory, will give you access to a filter to select the particular grid object which you want, and only at that time it will read only those sub-pieces which you care for. Echo. This is a big difference really between the two softwares, and keep it in mind if you're doing large decomposed simulation types. Then there are often the question, the people doing climate, the people doing geophysics, etc. Can the software read my data and display it in spherical or cylindrical fashion? The answer is no. There's no. The reason is the VTK objects of the pipeline don't have a native object for a spherical grid or a rectilinear grid. But we can still do it. We have to transform the data into spherical space at the time of the display. So this can be done, and I can help you with that as well. There are the so-called XML VTK files. This is the new generation of the VTK file format. I'll give you a couple of examples here. Here I have an unstructured grid partitioned among 4 different submeshes, and each of those submesh, is an independent file, and it's called a piece. This has the advantage that I can read a single piece by telling the software to open only a single piece, or I can read the composite setup. If we have a structured grid, here we have an example where the data set is partitioned among multiple objects, and we see that we specify the IJK indices of the partition, and we actually have some overlap. So this is how we would implement ghosts. In this particular case, we could actually store the ghost cells into our data. This could be useful mostly when we debug a simulation. We actually want to see the ghost cells that are stored and that are exchanged. HSPart is something specific to particle data, and this is a case where I would actually often put multiple time steps into the same file, and there's a convention where you can store each of those time steps like this, with this particular name, step, pound sign, and then all your different time steps. And you can decide to store 1 or 10 or 100 time steps per file, and then give me multiple HSPart for the full temporal distribution. Here again, I have the Python script for you to test, and I will distribute that. You don't have to create it by hand. This illustration here is something specific to the Visit software, which we will show tomorrow. It actually shows you here those little particles, those little spheres. They are the data set at one particular time step. And in this particular filter, we actually connect the time steps between each other to see the evolution of those particles in space. So this is just a benchmark example, nothing physical. I've taken, this is the Python script which I have created for you. It takes those little particles around a circle and it moves them up and like this in a spiral. This is why when we connect them together, it shows this little cylinder. XDMF is yet another version, another specification of data using XML. Here's my advice. Use XDMF if you want to use ParaView, because we can do parallel visualization well. With Visit, it's not implemented correctly, so it's not working very well. XDMF is a way of partitioning the data into two different files. One of them is the XML file, which represents the metadata, so it's lightweight. And the other one, the heavy data, is written in HDF5 in a second data set. There. So there is an example quickly, an HDF5 file, which I look at inside the HDF viewer. Just a big table of three-dimensional data. And the XML description, that is the metadata. It actually gives me the dimensions of the grid, the type of grid. This is a 3D rectilinear grid. It gives me the X, Y, and Z coordinates of each of the axes. And right here, it gives me the path to an HDF5 file where the heavy data is stored under those particular characteristics. The advantage of this is that when we create the visualization pipeline, the pipeline only reads this. This is the ASCII description, lightweight, and only when we need to access the heavy data, we go to the HDF5 data volume. Here's another example for the curvilinear example where the XYZ coordinates are stored in one data set. The numerical solution is stored in multiple arrays here, as we can see. And the description in XML tells us that we have a 3D S mesh, which means structured but with explicit coordinates in space. All right, I'm good. I need to finish up with a summary. All this pipeline management will be hidden from us at the conditions that we have good metadata to represent our data. So back to the conventions, the CF conventions, for example. Here I can look at the content of the netcdf file, see what is available in the data, and then finally construct my visualization pipeline in correspondence to the logical organization of the data. Here are the questions to ask yourself before you store your data. And just because you are able to load your data in parallel doesn't necessarily mean that the visualization package has been able to decompose it in equal chunks among your different processors. So very often, mind you, I have the questions, people ask me, I'm running in parallel and it keeps crashing, and I don't understand why, because running in parallel, I should have n times as many 32 gigabytes, for example. My data fits completely, very easily with all this memory, Why does the visualization software crash? It's because in that case, people are using a format that is recognized, yes, but where the parallel implementation perhaps is missing a keyword somewhere in the storage, and it doesn't know how to do the distribution. So it loads everything on processor 0, everything else, all the other processors do nothing, and eventually it crashes. So this would be also a particular area where I have a lot of experience debugging people's visualization in parallel. All right.